Have you ever wondered what secrets an interstellar visitor brings when it hurtles into our solar system from the depths of another star system? Today, we'll dive deep into the incredible chemistry and breathtaking mysteries of Comet 3I/Atlas, the rare messenger now rewriting what scientists know about how worlds form across the galaxy. Across the Milky Way, most comets never leave the cold cradles where they were born. But once in a very long while, one of them is thrown out of its home system and sent drifting between stars. We call these objects interstellar visitors, and so far, we've only seen three: Oumuamua in 2017, Borisov in 2019, and now 3I/Atlas. Each one is a tiny fragment of a completely different planetary system, carrying frozen clues about alien worlds. 3I/Atlas was first spotted in early 2025 by a survey in Hawaii, moving on a path no ordinary comet could follow. Its orbit is hyperbolic and sharply tilted compared to the plane of our planets, clear evidence that it comes from far beyond the Sun's gravitational family. Since that first detection, telescopes across the world and in space have been racing to watch it as it swings past the Sun, brushes near Earth's orbit, and then escapes forever back into interstellar space. A new breakthrough study using ALMA and the James Webb Space Telescope has just revealed something stunning. 3I/Atlas is like nothing astronomers have ever seen before. Its molecules tell a story billions of years old, and its chemistry is changing how experts think about planetary nurseries far from our Sun. Let's look at some of the key discoveries. First, distinct outgassing patterns. 3I/Atlas emits hydrogen cyanide, HCN, straight from its core, while methanol, CH, a type of alcohol, bursts from icy grains in its coma. That means the nucleus is not a simple, uniform ball of ice. It's complex and heterogeneous, with different ices stored in different layers and released in different ways as the comet wakes up. Second, record methanol levels. The ratio of methanol to HCN in this comet is more than 100 times higher than what we see in typical comets from our own solar system. That suggests a completely different environment at its birthplace, a frigid, chemically unusual region around a distant star, where methanol ice could build up in enormous quantities. Third, extreme carbon dioxide. Observations with the James Webb Space Telescope show one of the highest carbon dioxide to water ratios ever measured in any comet. That points to 3I/Atlas having formed near a carbon dioxide ice line in its home system, where CO2, not water, was the dominant frozen ingredient. And fourth, surprising elements. 3I/Atlas is rich in nickel and shows unusual metal signatures compared to most comets we know. Those metals, liberated from dust grains in its coma, hint at a chemistry shaped by billions of years of exposure to cosmic rays and radiation in deep space. To understand how strange that is, imagine food instead of chemistry. Just as every region on Earth has its own rice recipe, every planetary system bakes its comets with unique cosmic ingredients. In our solar system, most comets are like traditional dishes: plenty of water ice, some carbon monoxide, a familiar balance of organics and dust. 3I/Atlas is the exotic recipe from far away, loaded with methanol, carbon dioxide, and metals in proportions we almost never see here. Hydrogen cyanide, that scary-sounding HCN, actually works as a reference spice for astronomers. Almost every comet we study contains some HCN, so it's a good baseline. Methanol is different. It forms on the surfaces of dust grains in extremely cold regions, where simple molecules can slowly combine over very long times. Finding a little methanol is normal, but 3I/Atlas is overflowing with it. In simple terms, if a typical comet is like rice cooked with a pinch of wine, 3I/Atlas is rice soaked in an entire bottle of strong liquor. Its chemistry is that extreme. This tells scientists that the comet probably formed in a part of its home system that was not just cold, but chemically special, maybe on the outer edge of its protoplanetary disk, where methanol and carbon dioxide could freeze out more efficiently than water. Combined with the high CO2 to water ratio, the emerging picture is of a planet-forming region very different from the one that built our own solar system. So, why does any of this matter? Each interstellar comet is a puzzle piece from a galactic recipe. 3I/Atlas shows us that planet nurseries in other star systems can be chemically diverse, and that directly changes our understanding of what makes worlds potentially habitable. If the building blocks of planets vary this much from system to system, then the possible types of oceans, atmospheres, and even prebiotic chemistry across the galaxy are far richer than we once imagined. The sky is not universal. The universe is a mosaic. 3I/Atlas will make its closest flyby of Earth in December, passing at a distance roughly twice as far as the Sun is from us. That's nowhere near a danger zone, but it is close enough for our telescopes to keep studying every molecule they can before the comet fades away into the dark. Right now, observatories are racing the clock. As 3I/Atlas moves away from the Sun, its activity will drop, its coma will shrink, and the chemical fingerprints in its gases will become harder and harder to read. This is a once-in-a-lifetime chance to analyze the chemistry of a truly alien comet up close. And remember, 3I/Atlas is not an alien spaceship. It doesn't need to be. As a natural comet from another star, it's already far more valuable, a sealed sample from a place we will never reach, carrying a chemical story that began before our sun was born. When it finally disappears back into interstellar space, we'll be left with spectra, numbers, and models, but also with a deeper realization. Our galaxy is not one story repeated a trillion times. It is a library of different experiments in planet building. Every time an interstellar comet passes through our skies, the universe quietly hands us one more page to read. If you want to discover what alien chemistry really looks like, and what secrets the next interstellar visitor might reveal, subscribe to the channel, hit the bell, and join our journey through the cosmos. You can find the original study by Roth and colleagues, along with more cutting-edge research on 3I/Atlas.